Welcome to the Blast from the Past series by IMS, in which we are looking at previous year CAT questions, primarily from the year of 2003 to 2008. In today's session, let's look at some more questions from numbers. So here's our first question. For the product n times of n plus 1 times of 2n plus 1, n belonging to natural numbers, which one of the following is not necessarily true? Not necessarily true means it may be or may not be true, which also means that the other three options will definitely be true. Now, if you go through all the four options, picking the answer over here is very, very simple and straightforward. The first option says that the product is even. Second option says that the product is divisible by 3. Third option says that the product is divisible by the sum of the square of first and natural numbers. And the last option says that the product is never divisible by 237. Now, it's very easy to understand that my product is n times of n plus 1 times of 2n plus 1. If I put n is equal to 237, the product will be definitely divisible by 237. It will be 237 into something and definitely be divisible by 237. So the product is never divisible by 237. We can say that it is wrong. In fact, it will be wrong not only for n is equal to 237, when n plus 1 is 237, which means n is equal to 236, or when 2n plus 1 is 237, which means 2n is 236, n is 118. Even in those two cases, the product will be divisible by 237. So the product is never divisible by 237. Even common sense tells us that is not the case. It has to be divisible when n is equal to 237. So option 4 is my answer. We could have picked the answer directly, but if we were checking all the options one by one, we could do that as well and establish that the first three options are going to be necessarily true. So let us see why the first three options are going to be always true in this case. And hence we can say that option 4 will be the answer. So if I consider the first option, it says that the product is even. Now the product is n times of n plus 1 times of 2n plus 1. We know that n is a natural number, and we can see that n and n plus 1 are consecutive. So they are consecutive natural numbers. Consecutive natural numbers are always of different parity, which means if n is going to be even, then n plus 1 will be odd. And if n is going to be odd, then n plus 1 will be even, which means in either case, the product of these three terms is going to be even only. So the product is always going to be divisible by 2. Which means it is definitely or necessarily even, and hence this was not our answer. If you look at options 2, it says the product is necessarily divisible by 3. Now, for n, there are three possibilities: that it is a multiple of 3. If not, then on dividing by 3, it may leave a remainder of 1, or it may leave a remainder of 2. If I check all the three possibilities for n one by one, if you put n is equal to 3k, obviously the product becomes, if you put n is equal to 3k, then in that case, the product is definitely becoming divisible by 3. I've put n is equal to 3k, so n is 3k, n plus 1 is 3k plus 1, and twice of n, so twice of 3k, 6k plus 1. And you can see that this is definitely 3 into something, right? So this is necessarily divisible by 3 when n is a multiple of 3. Second possibility is n is of the form 3k plus 1. So if I put n is equal to 3k plus 1, then this is n. n plus 1 will become 3k plus 1 plus 1, that is 3k plus 2. And twice of n plus 1 will become twice of 3k plus 1, which is nothing but 6k plus 3. Again, you can see that I can take a 3 common from here. So this is again 3 into something. This is again 3 into something, which means this is also necessarily a multiple of 3 or divisible by 3. So when n is of the form 3k plus 1, then also the product is divisible by 3. Third possibility is n is of the form 3k plus 2. If I put n as 3k plus 2, n is 3k plus 2. n plus 1 will be 3k plus 2 plus 1. That is 3k plus 3. 2n plus 1 will be twice of 3k plus 2, which is 6k plus 4 plus 1, which is 6k plus 5. Again, you can see that these two terms are multiples of 3, which means I can take 3 common from here. And again, my product is 3 times of something. Again, my product is 3 times of something, which means it is again a multiple of 3 or necessarily divisible by 3, which means whatever be the form of n, the product of n plus 1 and 2n plus 1 is always divisible by 3, and hence this is necessarily true and not our answer. If we look at the third option here, it says the product is divisible by the sum of the square of first and natural numbers. Now the sum of the square of first and natural numbers, sigma n square, is given by the formula n into n plus 1 into 2n plus 1 by 6. If we divide the given product by this, what we have is n into n plus 1 into 2n plus 1. This is the product, and the formula is n into n plus 1 into 2n plus 1 by 6. And you will see that this is nothing but that 6 comes in the numerator. So this is nothing but n into n plus 1 into 2n plus 1 into 6 divided by n into n plus 1 into 2n plus 1. And we get a constant 6 without any remainders, which means this is also always divisible. So this is also not our answer. And as we discussed earlier, it's never divisible by 237 will obviously be not true when n is equal to 237. So option 4 is the answer. Three wheels can complete 60, 36, and 24 revolutions per minute. There's a red spot on each wheel that touches the ground at time 0. After how much time all these spots will simultaneously touch the ground again? If we consider any of the three wheels here, let's say this is the first wheel, let's call it A. It's saying that at the bottom, there's a red spot that is touching the ground. So there's a red spot over here that is touching the ground. Now, as the wheel makes, let's say 1/4 revolution, that red spot's going to reach here, right? When it makes half the revolution, the red spot will be here. When it makes 75% or 3/4 of a revolution, the red spot will be somewhere here. And when does the red spot touch the ground again? Only when the wheel completes one revolution. Again, when it completes 2 revolutions and so on. Which means every time the wheel completes an integral number of revolutions, the red spot is going to touch the ground. Now, in how much time is the first wheel completing a revolution? So it makes 60 revolutions. It makes 60 revolutions in 1 minute. 1 minute is 60 seconds, which means we can say that it's making one revolution in 60 divided by 60, 1 second. So after every 1 second, the red spot on the first wheel will be touching the ground. So after 1 second, it will touch, after 2 seconds, 3 seconds, and so on, right? Now, if we just call the other wheels B and C, and we know now that the red spot is going to touch when they complete integral number of revolutions. So if I look at B is making 36 revolutions in 1 minute, 60 seconds. So how much time does it take to make one revolution? One revolution it will complete in 60 by 36, which is nothing but 5 by 3 seconds. Likewise, we can also calculate for C. It is making 24 revolutions in 1 minute or in 60 seconds. So one revolution it is going to complete in 60 by 24 or 5 by 2 seconds, which means the red spot on A is touching the ground after every second, 1 second, 2 seconds, 3 seconds, and so on. The red spot on B is touching the ground after every 5 by 3 seconds. So 5 by 3 seconds, then again another 5 by 3, so 10 by 3 seconds, 15 by 3 seconds, 20 by 3 seconds, and so on. The red spot on C is touching the ground after every 5 by 2 seconds. So 5 by 2 seconds, 10 by 2 seconds, 15 by 2 seconds, and so on. What we need to find is after how much time all the spots simultaneously touch the ground again. We know that the red spot on wheel A is touching the ground. That time is a multiple of 1. When the red spot on wheel B is touching the ground, that's a multiple of 5 by 3. And when the red spot on C is touching the ground, that's a multiple of 5 by 2. Now, because we want all of them to simultaneously touch the ground, that means that time or that number needs to be a common multiple of 1, 5 by 3, and 5 by 2. Okay, so that is going to be nothing but the least common multiple if we are looking for the first time when the red spot is touching the ground simultaneously again. So let us find the LCM of the timing of the three wheels, which is 1, 5 by 3, and 5 by 2. Now, how do we find the LCM of fractions? LCM of fractions in their simplest form is nothing but LCM of the numerators upon HCF of the denominators. So LCM of 1, 5 by 3 and 5 by 2 will be nothing but LCM of 1, 5 and 5 divided by HCF of 1, 3 and 2. So LCM of 1, 5 and 5 is 5 and HCF of 1, 3 and 2 is 1. 5 by 1 or 5 seconds is the required answer. And you will see that there is no such option called 5 seconds. So even though such mistakes are not very common in CAT, but sometimes they do happen, which means when this particular question was asked in CAT, all the 4 options were incorrect. So the correct answer over here will be 5 seconds. So let's look at the next question. It says at a bookstore, modern bookstore is flashed using neon lights. The words are individually flashed at the intervals of 2.5 seconds, 4 whole 1 by 4 seconds, and 5 whole 1 by 8 seconds, respectively. And each word is put off after a second. The least time after which the full name of the bookstore can be read again is. So what the question is saying is that there are 3 words. Each of them has a neon light. So like the word modern, the neon light is on for 1 second. Then it is off for 2.5 seconds. Then again, it is on for 1 second. Then again, it is off for 2.5 seconds. Same way, book, the light is on for the light is on for 1 second. Then it is off for 4 whole 1 by 4 seconds. Then again, it is on for 1 second, off for 4 whole 1 by 4 seconds. And same way for store, it's on for 1 second and off for 5 whole 1 by 8 seconds, respectively. If the words flash together initially, then after how much time all of them can be read for full 1 second again, which means when do they flash together again? Okay, so if you see modern, it is on for 1 second. So initially it is on from 0 to 1 second, and then it is off for 2.5, 5 by 2 seconds. So 1 plus 5 by 2, that is nothing but 7 by 2. So 1 to 7 by 2 seconds is going to be off. Then 7 by 2 seconds, it will again turn on and it will be on for 1 second. So 7 by 2 to 9 by 2 seconds, it's going to be on. Then 9 by 2 plus 5 by 2, it's again going to be off. So 9 by 2 seconds to 5 by 2 means 14 by 2 or 7 seconds, it will be off and so on. So you can see that this is one cycle of the word mod. It's on and off. It's a cycle of 7 by 2 seconds. Then again, it is on for 1 second, off for 2.5 seconds. It's again a cycle of 7 by 2 seconds, right? So this 7 is nothing but twice of 7 by 2, right? So it's a cycle of 7 by 2 seconds for the word modern. Likewise, we can calculate the cycle for the other 2 words. So if we look at book, it is on from time 0 to time 1 second. And then it is off for 4 whole 1 by 4, which when you convert to improper fraction, 17 by 4 seconds. So 1 second, it is turned off. And for next 17 by 4 seconds. So 1 plus 17 by 4, that is 21 by 4 seconds. It is off. Then it will be again on for 1 second. So 21 by 4 plus 1 second is 25 by 4 seconds. It is on. And then again from 25 by 4 seconds, it again turns off for another 17 by 4. So 25 by 4 plus 17 by 4 is 42 by 4 seconds. It is off. And again, you can see this 42 by 4 is nothing but twice of 21 by 4, because there was one cycle of on and off and it lasted 21 by 4 seconds. So the modern cycle was 7 by 2 seconds. The book cycle is 21 by 4 seconds. Likewise, we can calculate the cycle for the word store. Again, you can see that the word store is on from 0 to 1 second. Then it is turned off for 5 whole 1 by 8 seconds, which if you convert to improper fraction, that's 41 by 8 seconds. So 1 plus 41 by 8 is 49 by 8. So here it is on and here it is off. Then again, it is on for another 1 second. So 49 by 8 plus 1 is 57 by 8 seconds. It is on. And then again, it is off for another 41 by 8 seconds. So 57 by 8 plus 41 by 8 is nothing but 98 by 8 seconds. And again, we can see 98 by 8 is nothing but twice of 49 by 8, which means this was one cycle of the store on and off, and it lasted 49 by 8 seconds. Okay, which means the word modern, we can say it is turning on after every 7 by 2 seconds. the word book is turning on after every 21/4 seconds, and the word store is turning on after every 49/8 seconds. Now, what we need is we want to read the full name of the bookstore again, which means we want all the three words to turn on together, which means the time that we are looking for, it has to be a multiple of 7/2 for modern. It also needs to be a multiple of 21/4 for book, and it also needs to be a multiple of 49/8 for store, which means we are looking at a common multiple of these numbers. We are looking at a common multiple of these three timings. And because we need the least time after which we can read the word, we are looking at the least common multiple, which in other words means we are trying to find the LCM of 7/2, 21/4, and 49/8. What we need is LCM of 7/2, 21/4, and 49/8. Now, LCM of fractions is LCM of numerators upon HCF of denominators. So what we need to find is LCM of 7, 21, and 49 divided by HCF of 2, 4, and 8. So LCM of 7, 21, and 49, that will be 147. And HCF of 2, 4, and 8 is going to be 2, which means the required time is 147/2 or 73.5 seconds. That is the required answer. Okay, so let's look at the next question. It says 3 pieces of cakes of weights 4.5 pounds, 6 whole 3/4 pounds, and 7 whole 1/5 pound respectively are to be divided into parts of equal weight. Further, each part must be as heavy as possible. If one such part is served to each guest, then what is the maximum number of guests that could be entertained? Now, please remember that numbers which divide a given number are factors. 3 pieces of cakes of weight are to be divided into parts. Numbers which divide a given number perfectly without leaving any remainder are factors. So when I divide, let's say 4.5 pounds, if suppose I'm dividing it into a half-pound pieces, then I can get 9 pieces from there, right? And we can say that if we are not looking at only integral factors, then we can say that half is a factor of 4.5, right? So numbers which divide a given number perfectly without leaving any remainder, they are factors. And what we are trying to find here is factors of 4.5. If we convert that to improper fraction, that is 9/2. Let's call our 3 pieces as A, B, and C. So A size is 9/2 pounds. B is 6 whole 3/4. When converted to improper fraction, that is 27/4. And C is 7 whole 1/5, which is nothing but 36/5. Now, we know that we are looking at pieces of these cakes. So which means we are looking at factors of, so for A, we need factors of 9/2. For B, we need factors of 27/4. And for C, we need factors of 36/5. But we know one more thing. All these pieces are of equal weight. Equal weight means we are looking at common factors. We want common factors of A, B, and C. Common factors of 9/2, 27/4, and 36/5. One more thing, it says that not only should these pieces be of equal weight, but each piece must be as heavy as possible, which means we are looking at the highest common factor, as heavy as possible. Highest common factor is nothing but HCF, which means this is nothing but a word problem where I'm supposed to find the HCF of 9/2, 27/4, and 36/5. What we need is HCF of 9/2, 27/4, and 36/5. How do we find HCF of fractions? That is nothing but HCF of the numerators. So HCF of 9, 27, and 36 divided by LCM of the denominators. So LCM of 2, 4, and 5. Now HCF of 9, 27, and 36 will be 9 itself. LCM of 2, 4, and 5 is going to be 20. Okay. So my HCF of these fractions is 9/20. Now what does this 9/20 represent? This represents the size of each piece. 9/20 pounds is the size of each piece. But this was not my question. They're not asking me what is the size of each piece. they're asking me that we are serving one piece to each guest. What is the maximum number of guests that we can entertain? Okay, so now we've got the size of each piece. Let's see from the cake A, how many pieces can we cut? So the size of A is 9 by 2 and the size of each piece is 9 by 20. So the number of pieces that we can cut from A, the number of pieces that we can cut from A will be nothing but size of A divided by the size of each piece. So if you simplify this is nothing but 10. So from the cake A, we can cut 10 pieces. Similarly, how many pieces can we cut from the cake B? So that will be nothing but size of cake B divided by the size of each piece. So again, if we simplify this is nothing but 27 by 4 into 20 by 9. 9 and 27 cancels. 4 and 20 cancels. 3 into 5 is 15. How many pieces can we cut from the cake C? Size of cake C, which is 36 by 5, divided by the size of each piece, 9 by 20. This is nothing but 36 by 5 into 20 by 9. Again, you will see that this number is 4 into 4, 16. So from cake A, we can cut 10 pieces. From cake B, we can cut 15 pieces. From cake C, we can cut 16 pieces, which means total how many pieces can we cut? So total number of pieces is nothing but the summation of these three values. So total number of pieces that we can cut is nothing but total number of pieces that can be cut from these three cakes is nothing but 10 plus 15 plus 16, which is 41 pieces. And as the question says, one piece is served to one guest. So if I got 41 pieces, we can serve maximum of 41 guests, which means 41 guests is our answer. If you look at the options 54, 72, and 20, they do not match, which means none of these is the required answer. 41 is the correct answer over here. Let us look at the next question. It says if n is any positive integer, then n cube minus n is divisible always by 12, never by 12, always by 6, and never by 6. Now, one thing that we can say for sure over here is that if a number is divisible by 12, then it will definitely be divisible by 6. So if always by 12 is the correct answer, then always by 6 will also be correct. And because there will be only one correct answer, we are sure that always by 12 cannot be the answer. Similarly, if you look at the remaining options, if a number is not divisible by 6, it cannot be divisible by 12 either, right? It has to be first divisible by 6, then only it can be divisible by 12, which means if it is never divisible by 6, then it will never be divisible by 12 also. So never by 6 is also not possible, right? If the number is never divisible by 6, then in that case, never by 12 will also become true. So again, two answers, which is not possible. So never by 6 is also not the answer. Now, is the answer always by 6 or is the answer never by 12? How do we decide that? So it says n is any positive integer, n cube minus n. Now, n cube minus n, we can write this as n times of n square minus 1. N square minus 1, this can be further factorized as n plus 1 into n minus 1, which means n cube minus n, the complete factorization is nothing but n minus 1 into n plus 1. We can see that n minus 1, n, and n plus 1, they are positive integers. If n is positive integer, n minus 1 and n plus 1 are also positive integers. And these are consecutive natural numbers. These are going to be consecutive natural numbers. Okay, which means because these are three consecutive natural numbers, one of them is definitely divisible by 2 and one of them is definitely divisible by 3, which means the product of these natural numbers will definitely be divisible by 2 into 3, 6. So this product is always going to be divisible by 6, which means option C is our answer. Okay, we could have also made use of the property here that the product of n consecutive natural numbers is always divisible by n factorial. One more thing that we could have done is, once we were left with options B and C, we could have taken n as, let's say, 2. So if I take n as 2, then 2 minus 1 is 1, 2, and 2 plus 1 is 3. So the product was coming as 6, which is divisible by 6, but it is not divisible by 12. So we could have taken an option and tested, but please remember that options might satisfy more than one, substitution of values might satisfy more than one option. So it's better to use a proper method here. So either we can just factorize as we have done, and then we can say that because these are three consecutive natural numbers, one of them will be divisible by 2 and one of them will be divisible by 3, or we can make use of a similar property. So option 3 is the answer. Now, a very, very similar question was again asked in CAT. So let's look at that question also. Only difference was it says if n is any odd positive integer. So n is any odd positive integer. And another difference was they said n into n square minus 1. This is always divisible by. This is going to be always divisible by. And our options were 96, 48, 24, and none of these. Again, you can understand that if a number is divisible by either 96 or 48, 24 is a factor of both of them. It will also always be divisible by 24. So if 96 is my answer, 48 and 24 will also be correct. If 48 is my answer, 24 will still be correct, and we do not have more than one correct answers, right? Which means 96 and 48 cannot be the answer. The only thing we needed to check was, is it always divisible by 24 or not? Again, n into n square minus 1 is nothing but n into n minus 1 into n plus 1, which means this is the product of three consecutive natural numbers. This is again the product of three consecutive natural numbers. Not only that, in this case, we know that n is odd. Because n is odd, n minus 1 will be even, and n plus 1 will be the next even number. N plus 1 is going to be the next even number. So for example, if n minus 1 is 8, then n plus 1 will be 10. N minus 1 is 14. N plus 1 will be 16. So n plus 1 is the next even number, which means one of the numbers is definitely divisible by 2 and the other is definitely divisible by 4. Not only that, because these are three consecutive natural numbers. These are three consecutive natural numbers. One of them is definitely divisible by 3. Which means the product of these numbers will definitely be divisible by 2 into 4 into 3, which means 24. So any such product is going to be always divisible by 24, not necessarily by 48 and 96. 24 was our answer to this CAT question. So very, very similar question you can see, and it has been asked in 2 different years. Let us look at the next question. The number of positive integers n in the range 12 is less than equal to n is less than equal to 40, such that the product n minus 1, n minus 2 up to 1 is not divisible by n is how many numbers? So the product n minus 1 into n minus 2 up to 1 is nothing but n minus 1 factorial. So basically the question is saying for how many values of n between 12 and 40, n minus 1 factorial is not divisible by n. Now, what we need to understand here is that n minus 1 factorial will not be divisible by n only if n is a prime number. Only if n is a prime number, it is not going to be divisible. Otherwise, it will be definitely divisible. Why? Because if n is not a prime number, it's a composite number. All the factors of n will be between 1 to n minus 1 other than n itself. And n minus 1 factorial contains all those factors. So n minus 1 factorial will be definitely divisible by n. If it is not divisible, then n has to be a prime number, which means the question simply translates to in the range 12 to 40, how many prime numbers are there? So 13, 17, 19, 23, 29, 31, and 37. There are a total of 7 prime numbers in this range, and hence 7 is our answer. But there could have been an interesting twist in the tail if suppose the question was 1 is less than equal to n is less than equal to 40. Again, while the definition still remains the same, that if n minus 1 factorial is not divisible by n, then n should be a prime number. And then if I look at prime numbers between 1 and 40, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and 37. There are a total of 12 prime numbers. But in this case, 12 would not have been the answer because there is one composite number for which n minus 1 factorial is not divisible by n. N minus 1 factorial is not divisible by n when n is equal to 4, even though n is a composite number. 4 is a composite number here, which means the answer in this case would have been 13. So it's good to know that 4 is one composite number which is not divisible by n minus 1 factorial. But otherwise, this property is only true for prime numbers. Okay, this is our next question. A young girl counted in the following way on the fingers of her left hand. She started calling the thumb 1, the index finger 2, middle finger 3, ring finger 4, little finger 5. Then reverse direction. Again, she called the ring finger 6, middle finger 7, index finger 8, thumb 9, and then back to the index finger for 10, middle finger for 11, and so on. She counted up to 1994. And she ended on which finger? This is our question. So a very interesting number series or progressions question. One way of solving this could be we can just try to figure out for each of the fingers what numbers is she counting on them and what form do those numbers take if they follow a particular pattern. So like for example here, she's counting the thumb on 1. Then she's counting thumb on 9. Then again, you can see that 10 is index finger, 11 is middle finger, 12 will be ring finger. Then in that case, 13 will be the little finger. Then 14 is again the ring finger. 15 is middle finger. 16 is index finger. And 17 is the thumb again. So you can see that it's an arithmetic progression with a common difference of 8. Then if you look at the index finger, she is counting 2. Then again, you can see that she does count index finger on 8 also. Then she does count the index finger on 10 also. And then 11 is middle finger, so 12 will be ring, 13 will be little, 14 will be ring, 15 will be middle, and 16 again will be index finger. Then 17 will be thumb, and 18 again will be index finger. So you can see two alternate progressions here, 2, 10, 18, etc., 8 and 16, etc., both with a common difference of 8. Okay, so because you can see that common difference for each finger turns out to be of the form 8 only, like even if we check for the middle finger, you can see that she's counting the middle finger on 3, then she's again counting the middle finger on 7, then she's again counting the middle finger on 11, and then you can see that middle finger is 11, so 12 will be ring, 13 will be little, 14 will be ring, and 15 will again be middle. So common difference of 4, again you can see that 4 is nothing but a factor of 8 only. Similarly, if you look at the ring finger, she's counting the ring finger on 4 first time, then she's counting it on 6, then again she's counting it on 12. Then again, if 12 is ring finger, 13 will be little and 14 will be ring again. So again, you can see two alternate progressions with a common difference of 8, right? And if we look at the little finger, she's counting the little finger at 5, then she's counting the next time at 13, and then you will see that she counts it at 21. So again, an AP with a common difference of 8, which means all the APs are either with a common difference of 8, or there are alternate APs with a common difference of 8, or there's an AP with a common difference of 4, which is also a factor of 8, which means we can just define a cycle of 8 over here. So if you look at the thumb, the numbers on which she's counting the thumb, they are nothing but 8k plus 1 form, which means when you divide these numbers, you are going to get a remainder of 1. If you look at the index finger, there are two alternate progressions, as we can see, 2, 10, 18, etc., and 8, 16, etc., which means 8, 16 is of the form 8k, and 2, 10, 18, when you divide these kind of numbers, they are nothing but multiple of 8 plus 2. If you look at the middle finger, it is nothing but 8k plus 3 form, 3, then 11, etc. So again, two alternate progressions. One is of the form 8k plus 3. Second is 7, 15, etc. So this is of the form 8k plus 7. If you look at the ring finger single progression, or in fact, again, there are two alternate progressions. 4, 12, 20 is 1. So that is of the form 8k plus 4. And the other one is 6, 14, etc. That is of the form 8k plus 6. And the little finger, there's a single progression, 5, 13, 21. That is of the form 8k plus 5. So you can see that we have all the numbers in the form of multiple of 8 plus a particular remainder. She has counted up to 1994. If we divide 1994 by 8, we are getting a remainder of 2 over here, which means 1994 is of the form 8k plus 2. And 8k plus 2 form of numbers she is counting on the index finger. So index finger is the required answer. Now, do I really need to list all the progressions here? Well, this is a perfect method and it does tell you the form for each and every finger. But do I need to do for all of them? Basically, if I do for only the thumb also, I can easily get my answer. So once I have just counted for the thumb, let's say, and I know that she's counting thumb on 8k plus 1 form, what we could have done from here is, because she's counting up to 1994, we could have just seen what is the largest multiple of, or what is the largest number of the form 8k plus 1 that is less than or equal to 1994. And from there, we could have got our answer much faster. So if you just divide 1994 by 8, as we saw just now, it leaves a remainder of 2, 1994. If we divide by 8, it leaves a remainder of 2. And we need 8k plus 1 form, which means 1993 will be the largest number less than or equal to 1994, which is of the form 8k plus 1. Which means 1993, she would be counting on her thumb. And every time she counts thumb, the next finger that she's counting is the index finger. So 1994, she is going to count on the index finger, which means without trying to list the progression or the series for each and every finger, simply by following the thumb, because every time she's counting thumb, the next finger that she's counting, or the one that she's counting before the thumb, in either case, that is the index finger only. Okay, so 1994, she is definitely going to count on the index finger. Index finger is the required answer here. Let us look at the next question. The sum of 4 consecutive 2-digit odd numbers when divided by 10 becomes a perfect square. Which of the following can possibly be one of these 4 numbers? Now, because they're asking you a possible answer, we could have also solved this question using options. So like if you look at the first option, it says 21, sum of 4 consecutive 2-digit odd numbers. Now, what will be the consecutive 2-digit odd numbers that involve 21? So it could be 15, 17, 19, and 21. But please remember that the sum has to be divisible by 10, which means it has to end in 0. You can see that 9 plus 1 ends in 0, but 5 plus 7 does not. This cannot be my answer. Then if I look at the next 4 consecutive, it is 17, 19, 21, and 23. And you can see that this time the sum does end in 0. If I just calculate the sum, it's coming to 17, 36, 57, 80. 80 when I divide by 10, I get 8, which is not a perfect square. Next series is 19, 21, 23, and 25. And again, you can see that the sum is not ending in 0, which means this cannot be my answer. Next series involving 21 is 21, 23, 25, and 27. Again, you can see that this does not end in 0. This also cannot be my answer, which means option 1 cannot be my answer. These are the only series that involve 21 and they've got 4 consecutive 2-digit odd numbers. Now, as far as 25 is concerned, we've already covered 2 series of 25 and we know that they're not the answer. Next series that involves 25 is 23, 25, 27, 29. Again, you can see that 3 plus 7 ends in 0, but 5 plus 9 does not. This is also not the answer. And the next series involving 25 is 25, 27, 29, and 31. Again, 9 plus 1 ends in 0, but 5 plus 7 does not. This is also not my answer. If you look at the third option over here is 41. Again, the series involving 41 can be 35, 37, 39, 41. Again, 9 plus 1 ends in 0, 5 plus 7 does not. The next series involving 41 can be 37, 39, 41, and 43. 7 plus 3 ends in 0, 9 plus 1 also ends in 0. If we find the sum, 37, 39 is 76, plus 41 is 117, plus 43 is 160. If we divide 160 by 10, we get 16, which is a perfect square. This is the answer. So we could have answered making use of the options. Of course, it does take a little bit time, but we could have answered using the options. And there's a better way of also answering this question, because we are talking about 4 consecutive two-digit odd numbers. Let's say our numbers are of the form 2k minus 3, 2k minus 1, 2k plus 1, and 2k plus 3. So they have a difference of 2. They are consecutive odd numbers, right? What is the sum of these numbers? If you add these numbers, minus 3 plus 3 minus 1 plus 1 gets cancelled. The sum is 8k. Now they are saying that this sum 8k is divisible by 10. Now you can see that 10 is nothing but 2 into 5. 8 is divisible by 2, but it is not divisible by 5, which means for 8k to be divisible by 10, k will be a multiple of 5. Let's say k is equal to something like 5m. So in that case, my number becomes, or my sum of numbers becomes 8 into 5m, 40m, right? And we also know that this number, when we divide by 10, we get 4m. So that 4m is a perfect square. Now we know that 4 is a perfect square. So which means m will also need to be a perfect square only, which means m can be 1, m can be 4, m can be 9, and so on. If I put m is equal to 1, my sum is becoming 40 into 1, which is nothing but 40. So my sum is 40. For 40, this will be true. Now, please remember, if the sum is 40, the average will be 10, which means my consecutive odd numbers will be 7, 9, 10, 11, and 13. So the average is 10, right? So 7, 9, 11, 13 was one set of numbers which would have satisfied this property. Again, m can be the next perfect square, which is 4. So if I put m as 4, my sum of numbers becomes 160. Again, the average becomes 40. If average is 40, my consecutive odd numbers will be 37, 39, 41, and 43. Right, and here my sum is coming to 160, and you can see that 41 was there in the options. So this is my answer. So we could have solved like this also, and we could have also made use of the options to get the answer. Okay, this is our next question. Consider 4-digit numbers for which the first 2 digits are equal and the last 2 digits are also equal. How many such numbers are perfect squares? I think we'll take this again. So let's look at the next question. It says consider 4-digit numbers for which the first 2 digits are equal and the last 2 digits are also equal. How many such numbers are perfect squares? Which means it's saying that it's a 4-digit number and the first 2 digits are equal and the last 2 digits are also equal. So the number is of the form AABB and it is also a perfect square. Okay, so how many such numbers are possible? Now, knowledge of perfect squares will be of great help over here. So in fact, if you know that 88 square is equal to 7744 is the only solution to this question, you could have marked your answer as 1 directly. Option 5, 1 as your answer. Could have marked it directly. So knowledge of numbers is going to be of great help. If you do not know this, we know that 4-digit perfect squares will be between 31 square and 99 square. Now, quickly going through the squares till you come up with such an answer was also a possibility, but you can understand that because the answer turns out to be 88, that would have taken a lot of time. 31, 32, 33, up to 88, it might have taken a good 5-6 minutes. So definitely not the best method. Either you need to know this. If you don't know this, then how can we solve? See, AABB, what kind of number is this? You can see that the sum of alternate digits is the same, which means difference between sum of alternate digits is 0, which means AABB is a multiple of 11. It is divisible by 11. We could have also understood that by simply writing the place value of this number. So like 1100A plus 11B. So we can say that this is definitely divisible by 11. Okay. Now, please understand that there are only specific values that B can take. We know that a perfect square does not, it can end in 0 and it can also end in 2 zeros. But if it ends in 2 zeros, then for the sum of A plus B to be divisible by 11, A will need to be 11. or 22 or 33, but A is a digit. So which means B cannot be 0 over here. B cannot be 0. Now, while perfect squares do end in 1, but when they end in 1, whenever they end in 1, the tens digit is even. So they can never end in 1, 1. They cannot end in 1, 1. So 1 is not a possibility. Perfect squares do not end in 2, not possible. Perfect squares do not end in 3, not possible. Perfect squares do end in 4. And when they end in 4, like 144, or 324. So whenever they are ending in 4, the tens digit is again even over there, which means 44 is a possibility. So B can be 4. Now, if B is 4, then in that case, for A plus B to be divisible by 11, A can be 7. Okay, if A plus B is 11, A is 7. If A plus B is 22, the next multiple of 11, A is going to become 18, and 18 is not a digit. So A is 7, B is 4 is one possible solution. One such number is 7744. Now, again, can B be 5? Because we need to find how many such numbers. So let us continue to check. Can B be 5? While perfect squares can end in 5, but whenever they end in 5, the tens digit is 2 only. So they cannot end in 5, 5. That is not possible. Perfect squares can end in 6 also, but whenever a perfect square ends in 6, the tens digit is always odd. So it cannot end in 66, right? So this is not possible. Perfect squares do not end in 7. Perfect squares do not end in 8, while perfect squares can end in 9. Whenever perfect squares end in 9, the tens digit is always even. So they cannot end in 99, which means this is not one possibility. This is the only possibility. 1 is the required answer. Okay, let's look at the next question. What are the last two digits of 7 raised to 2008? So again, you can see this is a CAT 2008 question. Last two digits of 7 raised to 2008. Now, there are multiple ways we can solve this question. 7 raised to 2008. Just like the unit digit cyclicity, the last two digits also observe a pattern or a cycle or a cyclicity or a cycle. So we could have identified the cycle of 7, like 7 raised to 1, it ends in 7. The last two digits are 0, 7. We can say it's a single digit number. 7 raised to 2 is 49. 7 raised to 3 is 343. The last two digits will be 43. 7 raised to 4 is 2401. The last two digits are 001. 7 raised to 5, when you calculate the last two digits, it is again 07, which means that the last two digits are repeating after 4 steps. So we can say that the last two digit cycle of 7 is 4. The given power over here is not 4, it is greater than 4. As we do in all cyclicity problems, we just divide the cycle by 4. When we divide the cycle by 4, the remainder in that case is 0. Remainder 0 means the last two digits of 7 raised to 2008 will be same as the last two digits of 7 raised to 4, which is 0, 1. So 0, 1 is the required answer. So one way of solving this question is pattern method. What we've done just now, this is the pattern method. Let us look at another way of solving this question. So see, 7 raised to 2008. We can write this as 7 square raised to 1004. 7 square is 49, right? 49 can be written as 50 minus 1, right? Now, by binomial expansion, when you expand this, so your first term will be 1004 C0, 50 raised to 1004 minus 1 raised to 0. Then second term will be 1004 C1, 50 raised to 1003 minus 1 raised to 1, and so on. Basically, it's easy to understand that because 50 ends in 0, till I have 50 power 2 or more, my value is ending in 2 zeros or more zeros, which means up to the third last term, I'm always having 2 zeros or more zeros here, which means we are going to get the non-zero digits only from the last two terms. So what are my last two terms? 1004 C 1003, 50 raised to 1, minus 1 raised to 1003, and 1004 c raised to 1004, 50 raised to 0, minus 1 raised to 1004, which is an even power, so it will be plus 1. Which means these are not going to really contribute anything, only zeros in the last two digits. I'm going to get my last two digits from here. Okay, now NCN minus 1 is nothing but N, so 1004, C 1003 is nothing but 1004, and 50 raised to 1 is 50, minus 1 raised to 1003 is minus 1. NCN is 1, right? So if we simplify this, 1004 into 50 is nothing but 50,200 negative minus 50,200 is what we are getting from here, plus 1. That is nothing but minus 50,199. We can say the last two digits of this are minus 99. Okay, because this is negative and last two digits is nothing but remainder on division by 100. So when the remainder is negative, we should add the divisor, which means what is the corresponding positive divisor here? It is 0. So 0, 1 is my answer. Over here, we are making use of the binomial method of remainders. This is not the only other way of solving this question. We could have used one more method of remainders over here. So we could have also made use of the Euler's theorem, right? Euler's quotient of n. So that is defined as n times of 1 minus 1 by a into 1 minus 1 by b and so on, where when you prime factorize a number, n is of the form a raised to p into b raised to q into c raised to r, etc. So a, b, c are the prime factors. Now the last two digits of any number are nothing but remainder on dividing the number by 100. This is nothing but remainder on division by 100. So if we just calculate Euler's quotient of 100, 100 is nothing but 2 square into 5 square. So what is Euler's quotient of 100? That is nothing but 100 into 1 minus 1 by 2 into 1 minus 1 by 5. So that is nothing but 100 into 1 by 2 into 4 by 5, which is 40, right? So Euler's quotient of 100 is 40. Now by Euler's theorem of remainders, a raised to phi n divided by n, the remainder is 1, right? So because we are getting Euler's quotient of 100 as 40, we can say that 7 raised to 40 divided by 100, the remainder will be 1 only, right? And 7 raised to 40, obviously the power is much greater than 40, it's 2008. But 2008, when you divide by 40, it goes 50 times and leaves a remainder of 8. Which means 7 raised to 2008 can be written as 7 raised to 40 whole raised to 50 into 7 raised to 8. Because 7 raised to 40 by 100 remainder is 1, 1 raised to any power is 1 only. From this division, our remainder will be 1, right? So which means we just need to calculate the remainder of 7 raised to 8 divided by 100. Now, 7 raised to 8 also you don't really need to calculate the value. 7 raised to 8 can be written as 7 raised to 4 into 7 raised to 4. So maximum we need to calculate 7 raised to 4 only. 7 raised to 4 is 2401. 2401 when you divide by 100, the remainder is 1. So the remainder will be 1 from here. Remainder will be 1 from here. 1 into 1, the remainder will be 1 from here. So we are getting remainder 1 from the first term. We are getting remainder 1 from the second term also, which means the remainder will be 1 because we need to write it as 2 digits. We are going to write it as 0. So 0, 1 is the required answer. And here we are making use of Euler's theorem of remainders. So there are multiple ways in which you can solve a question. The learning that you have to take is obviously you should be aware of the different ways of solving the question. And then you should know that what is the shortest way of solving a question and what is the limitation to that shortcut. Like in what cases I cannot use the shortcut and hence I have to make use of the longer way of solving. I hope you enjoyed the session. If you have any questions, any comments, any queries, you can just post it in the comment section and we will try to answer those. Thank you.